you see that? Well, they kind of plan ahead, and they've got to figure out what the missions are, and make sure they're ready to go. And everybody in the committee was retired. I mean, it was fascinating. This is the new NRC report on the future of NASA.
Oh, I saw the video. Yeah.
But I was looking at the committee, and it's like,
You were basically saying that and less on pesky old mission.
Right? Oh, good. What's that?
We're all here to see the soft shoe.
I didn't know Dan was going to do that.
Dan, you can go ahead and start. Dan? Go ahead and start.
Go ahead. Okay, thank you. Okay, for those of you who know me, I'm Dan Schwartz. I'm in the High Energy Astrophysics Division. For those of you who don't know me, I'd love to meet you and talk about X-ray astronomy. I'm absolutely thrilled today, on many levels, to introduce Pat Slane, director of the Chandra X-ray Center. I'm proud to work for him. What service has Pat done for Chandra that you may not be familiar with? Well, in the past year, he's conducted, actually past 4 years, a long, vigilant battle with the Chandra budgets cuts proposed by NASA, and so far we're saving the program. Actually, I thought we're a lot like Ukraine. We're up against a superior power. We're holding on. We have lots of important and influential outside support. As Associate Director for Science, he instituted a pre-doctoral program for Chandra and a Chandra Visitor Program. But those aren't actually what I'm thinking about. Pat's first task with AXAF, which evolved into Chandra, was to measure the reflectivity of iridium flats. These measurements proved the greater throughput of iridium compared to gold, which had been the standard coating for all X-ray mirrors. They were significant to allow for NASA to allow us to change the coatings of our mirrors from gold to iridium. Leon van Spaybroek, the AXAF project telescope scientist, pointed out that the value of this contribution was worth $80 million in terms of the increased throughput of the mirror compared to its cost. More concretely, in principle, this has allowed an extra dozen or so Chandra proposals to be accepted every year. That's 3 impacts on 300 careers. Pat is well known for his work on supernova remnants, pulsar wind nebulae, and associated element formation and dispersal and cosmic ray acceleration, all as mentioned in his citation as a fellow of the American Physical Society. Pat's from Milwaukee, Wisconsin. He got a bachelor's degree in physics in 1977 at the U of Wisconsin Whitewater campus. Then he taught high school physics and astronomy for 4 years. Never underestimate a school teacher. After a master's degree from the U of Wisconsin at Milwaukee in 1982, he continued his tour of the U of Wisconsin campuses with a PhD in physics from Madison. He then got a cold call from the AXAF project, inviting him to apply for a position on the team supporting the development of Chandra. I think he had other serious offers that he considered, but we are very fortunate that he came here after negotiating carefully that he could still root for the Milwaukee Bucks. Here to present selected highlights of 25 years of fantastic science, I give you Pat Slane.
Thanks, Dan. And of course, it should not go unsaid that that cold call came from Dan. And that on my interview, which I came in late, and anybody who knows me knows I usually come here at 6 in the morning. I was late that day and never got to meet Harvey Tannenbaum, and they still hired me. So, yeah, I'm going to take great pleasure and pride in talking about 25 years of really nice science with Chandra. I'm going to say right away, and then in the hallways after all of the people come up to me and say, but you didn't talk about, I'm not going to cover so much material that Chandra has contributed immensely to. And a lot of it is, stuff from people in this room. I apologize in advance, but you understand that there's just so much that we can cover in this talk. So I'm not going to make this an historical, segue through X-ray astronomy, but given the history of Chandra and the location, I do have to start with a little bit of it. And so things, in many ways started, though there were many groups working in X-ray astronomy, X-ray solar observations. It began in many ways with this instrument of Riccardo Giacconi's, which is a set of 3 Geiger counters with some scintillators above to act as a coincidence shield to reject particles coming in. Launched in a rocket to look for evidence of X-rays from the moon. It was known that there was X-rays from the sun. It was theorized that one could fluoresce from the moon, and you'd be able to see that as well. For reference, because this becomes important as we start talking, that's the size of that thing, okay, relative to me. That's, by the way, on display at the Udvar-Hazy Center in Virginia. What's the name of the town? I forget the name of the town. But near Dulles, correct. And so here's how it worked. It was on a rocket. The rocket flew up. It rotated around so that those Geiger counters spun around, each one scanning a different part of the sky. You can see from this picture where the moon is in the field of view. Notice, because it'll become important in a second, it also looked in the direction of Scorpius. It looked in a lot of different directions when it went up. Okay? The results of that are shown on the right. And there's 2 different counters with different thickness filters. The bottom one is the thicker filter. You can see that the moon was indeed detected as a bump here, arguably in both detectors, certainly in the top one. But there's this obvious other huge peak that was in the direction of Scorpius, and wasn't named this way at the time, but astronomers being the types that we are, the first X-ray source in the constellation Scorpius, it's Scorpius X1. And it's later discovered or learned to be understood to be a accreting binary system, a neutron star accreting from a companion star. It was also noticed that the detector count rate didn't go all the way down to 0. There was a kind of flat, diffuse X-ray emission, kind of seen in all directions. But this really bright source was the stunning part. And this is why this part of the historical story has to be told, because this is December 1962. There's one source, okay, that's known besides the moon and one extra solar system source. So that prompts this team to propose to NASA a 30-foot long telescope. By the way, that's from me to the back wall I measured this morning. 1.2 meter, well, 4 feet in diameter observatory to unfold X-ray astronomy for the world. They didn't get that. That was a bit of a big ask after discovering one X-ray source. But other missions came along, smaller ones, that demonstrated that this was all a legitimate field. And so in 1976, an unsolicited proposal was sent to NASA for funding to study a 1.2 meter X-ray telescope. This was again by Riccardo and by Harvey Tannenbaum. through the decadal survey in the 1980s, this concept was raised as the high-profile thing selected for space astrophysics. It became this, which, if you look back, isn't so wildly different in concept from what was started in 1963. So for those of you who don't already know, very quickly, what's special about Chandra and about X-ray astronomy? How do you make the telescopes work? So first of all, a typical parabolic mirror reflects light back to a focal point, and we're all used to seeing that sort of thing from telescopes to shaving. Well, I don't know about the shaving mirrors, but they tell me that's how it works. But X-rays don't do that. When X-rays come into this, don't put videos in here. Let's back up. I can tell the story without having to show the video. When X-rays are incident on a surface like that, they're just completely absorbed. And so I do need to see if I can get this to advance, and if I can't, I'll just wave my hands. So instead, what you have to do is glance the X-rays off of the surface at a very, very shallow angle, okay? About a degree or so, and then they can reflect. And then if you coat those surfaces with a high Z metal, they'll reflect even better. But to get them to just glance off of a surface means that you have to have, instead of the bottom of a paraboloid for your mirror, you have to have the walls of the paraboloid, okay? And if you cut off the bottom of a paraboloid and you just hold the walls and then you tip them to somebody, what you mostly see is a big hole in the middle, okay? Not a lot of collecting area. So if that's your mirror, you're not going to be able to detect very faint sources because you don't have a lot of area unless you make a smaller cylinder and put it inside the first one, and a smaller one, and a smaller one, and nest them like Russian dolls. The complication, not that there's only one or two, but one complication is holding mirrors like that to maintain their figure. If you take a big parabolic mirror on the ground, I mean, it doesn't matter how much it weighs, you can put an entire structure underneath it. But you've got these cylinders that you want to squeeze to hold together, but you don't want to squeeze to deform, and they're nested in one another, and then it turns out they have to go on a rocket and get into space. So it's very complicated to make them. To get the figure, one has to, like any mirror, grind it to the correct parabolic figure. To get the surface smooth, though, is really critical because the scattering, which gives you the haze around an image, is dependent upon the wavelength of the light that you're looking at. And for short wavelengths, if you don't want any scattering, you need a really, really smooth surface on very, very small scales. So the way that you build that, when I was in graduate school, I was on an experiment with Andy St. Georgi. Andy St. Georgi was the senior graduate student. I learned everything on that experiment and many other things from Andy St. Georgi. When I came here and was first learning about this, he explained how these things work. He said, well, you make an X-ray mirror by taking a giant cylinder of glass and polishing it until you run out of money. And then you measure it. And then once it's all done, you mount it together, nest these mirrors together after they've been coated, and then you bind them together into the set that becomes the mirror assembly. This is the results of the performance of the Chandra high resolution mirror assembly, what we call the HERMA. And what's plotted here is the encircled energy, the fraction of the energy incident on the mirrors as a function of radius. That is, how concentrated the beam of a point source is. And what you can see is that for a radius of smaller than an arc second, you get 90% of the photons for 1.5 keV X-rays, okay? On the right, on the upper right, I'm showing the ASIS detector. It's the workhorse camera for Chandra that we take more than 90% of our data with. On the bottom, you can see a 2x2 array of CCDs. That's the imaging array. And so for reference, the background on that detector is about 7 times 10 to the minus 7 counts per second per square arc second. So what that means is that in this point, in this resolution element here within an arc second, the background from that detector is 2 counts per resolution element per million seconds. So you can look at really, really, really faint things with Chandra and detect them significantly with 5 counts. And a lot of very important stuff that I'll show you comes with that capability. So of course, you bundle it up into a payload, you launch it. Chandra is in a highly elliptical orbit, 64-hour period. Its apogee is at an altitude of about 140,000 kilometers. And we take data with it. We send it down to the Deep Space Network, which sends it right over to our Operations Control Center in Burlington, where our crew does health and safety checks, first of all, then gets all of the data down, then turns around and sends up new commands, and we take the next person's, the next several days' worth of observations. That's how it works. This is what it looks like. The high resolution mirrors in the front, that's where the X-rays come in. Way in the back, 10 meters away, is the science instrument module with the cameras, the high resolution camera, which is an imager with very, very high resolution, so you can take pictures of point sources that, that make use of that incredibly high resolution of the mirrors. There's another camera that I mentioned before, the Advanced CCD Imaging Spectrometer. It is a CCD detector that not only has great imaging capability, but it also records the energy of each one of the X-rays so that you can obtain spectra, modest resolution spectra, as well as images with it. Back in the optical bench area, there are transmission gratings that can be swung into the beam to disperse the spectrum into high resolution spectrum. There are 2 arms of a set of gratings there, a medium energy grating and a high energy grating in this particular gratings device. And they can then turn the X-ray data into optical quality spectra, okay? So, that first source that was detected, remember that little haze that was sitting out at the edges? It turned out that lots of studies were done, and yeah, there really was this sort of diffuse-ish X-ray emission coming from all over the skies. As telescopes got better and better, it was recognized that at lower energies, many of those things were discrete point sources in the galaxy. At higher energies, the spectrum was a little different, and it wasn't clear what they were. So one of the points of Chandra was to establish the nature of that diffuse X-ray background and whether it was indeed diffuse. Within a very short amount of time after launch, deep observations of a patch of the sky were taken and shown that it was resolved into many, many different point sources. Ultimately, in this field, we accumulated up to 7 million seconds, detected over 1,000 X-ray sources, and by studying their counterparts, find that the vast majority of them are AGNs. The field of view of that detector was 17 by 17 arc minutes. There's 1,000 sources. More than half of those sources are supermassive black holes. What that tells you is that in the area on the sky covered by the full moon, there's 5,000 supermassive black holes, according to observations from Chandra. Well, that kind of sets the stage for, you know, the capabilities of the telescope, and one of the great first results of it resolving the X-ray background. As I mentioned at the outset, there's so much to talk about. There's so many things that Chandra has done that I can't get to all of them, but I'm going to break it into a little bit about stellar life cycles, a little bit about AGN feedback, and a little bit about cosmology. This is a ROSAT image of the Orion, the central region of the Orion Nebula. The ROSAT telescope was the highest resolution X-ray set of mirrors before Chandra flew. And it's looking at the center of the Orion Nebula. We all know what the Orion Nebula is. It's a region of new star formation. It's populated with lots and lots of young stars over a significant mass range. And you look at this and you say, well, I can see some of those stars, and maybe in the middle I see, I don't know, a haze of hot gas, or I don't know what's going on. But if you look at it with Chandra, you can see that it's populated with over 1,000 detected young stars. This is taken with the ACES detector. Remember, I mentioned that you can record we do record the energy of each one of the photons that comes in. So that means that we can decide for display purposes to say, let's make the high energy photons above some energy blue, and let's make the medium ones green, and let's make the low energy ones red, and then get a colored image that actually has physical meaning here, okay? So where we see the bluish stars, we're seeing stars whose emission from here, X-ray emission from here, is dominated by high energy photons. The greenish ones are medium, the reddish ones are low energy. And so immediately when you look at this, you can see either a distribution of temperatures of stars, or possibly some stars that are embedded in absorbing material. And so they appear blue because most of the lower energy X-rays have actually been absorbed out. Or some combination, and that's probably what you see is some combination. One way to get at what you're seeing is, and this is the one image that I wasn't sure would show up well with the windows open or with the shades open, but is to put the gratings in when you're looking at the Orion Nebula. So every one of these colored arms that you see here is a dispersed spectrum from one of the central bright sources in here. Actually, I'm telling a lie, which is all right. I'm going to do that all day long because I was a teacher, like I said, like Dan said. Actually, what's happening here is that these dispersed spectra are indeed from the stars in the center of this cluster. But if you think about it for a minute, they shouldn't have this wagon wheel shape, right? Because why would some go this way and why would some go this way? What happens is that this is 2 million seconds of observations with many individual observations added together. And some were taken with the camera this way, some were this way. I shouldn't say the camera, the whole observatory rolled this way, this way, this way. And so you have actually separation of many of the spectra by allowing you to do that. The point is that you can use the spectrometer on Chandra to get a lot more information about these stars than just the colors that you can see in the ACES image. And in this process, the group led here by Norbert Schultz has obtained 36 very high quality spectra of very young stars in a new star forming region, has identified in a handful of them Doppler broadening of 2 to 500 kilometers a second from apparent probably binary motions, as well as in some of them high temperature components that are hotter than what most corona models would have predicted. There's other things that have been uncovered about stars from Chandra observations. Some of the same team that did that first Orion observation with the ACES detector went on to look at 40 more star-forming regions, probably 39 more, and detected over 24,000 stars. They looked at variability and in particular for evidence of flares. And for over 1,000 of those stars, they found evidence of very powerful frequent flaring. Based on that information, they concluded that the level of energy coming out of those flaring activities was enough to make it very difficult to maintain atmospheres for exoplanets that would have been around those types of stars. Being more specific, observations that Chandra and Hubble did of Barnard's star, which we know does have an exoplanet, showed that, yeah, the quiescent X-ray and ultraviolet flux would allow a planet in the habitable zone to maintain its atmosphere. But the Chandra observations showed in the inset there by France et al. Evidence of flaring during the observations. And if that flaring is frequent, then it's not likely that those atmospheres would survive. Further along in the evolution of stars, we all know that when massive ones find the ends of their lives, that they collapse into sometimes black holes, sometimes neutron stars. And the Crab pulsar, especially for somebody of my age, was thought to be the prototype of what happens to a neutron star. You get this rapidly spinning, 30 times a second, highly magnetic, something several times 10 to the 12th Gauss rotating star, and that generates this wind of relativistic particles, and it lights up a nebula around it that we all know as the Crab Nebula. But what wasn't known is exactly how that picture unfolds. And when Chandra looks at the Crab, one sees very interesting things. You can see, I know I'm not supposed to point with the laser pointer, right? Because then nobody online can see that. True? So, all right. Yeah, I'll almost surely skip slides if I, by accident if I do that. But one sees the pulsar in the middle, okay? One sees a very distinct jet coming to the lower left. One sees on the inside a distinct ring, and then a bigger torus around that. So what's going on there? What's going on is that the neutron star is spinning around. It's generating the wind that I just described before. In the process, it accelerates particles, and some of them get confined into a jet and a counterjet that are along the rotational axis. And in the equatorial axis, there's an outflow that actually feeds most of the nebula. And that outflow feeds the entire Crab Nebula with relativistic particles, builds up this balloon of magnetic flux and relativistic particles, which of course then has a pressure to it. So as the next part of the wind is coming out of the pulsar and trying to enter that nebula, it's finding a pressure resistance. And so it forms a shock in the equatorial region, a standoff shock, where that happens. And that's that inner ring, okay? If you take the size of that ring, and if you take the spin down power of the pulsar, because we can observe it spinning down, and you take radio observations of the nebula and calculate the pressure, and you do the math and say, well, how big should the ring be? It's actually the right size. That's basically, it's obviously a little bit more complicated picture than that, but that's basically what's going on. And so what this image is showing you is the orientation of the axis of a rotating neutron star a very long way away. Not only which direction the axis is, like this, but that ring in the center should be round, okay? And it's not round. Why isn't it round? Because it's tilted into the sky. How much is it tilted into the sky? It's a nice high school trigonometry exercise to figure that out. So this Chandra image shows us all sorts of information about the Crab pulsar. And the geometry that one gets out of these resolved images with Chandra is incredibly important for other studies. Here's a quick example of that. Well, now I show you where all that stuff is with arrows. This is an image of Chandra on Nature Astronomy that doesn't know that north is up, so I'll fix their magazine by rotating it properly. Along with magnetic field vectors from IXPE observations from the polarization of the X-rays. And you can see that that toroidal structure from the equatorial expansion and injection of particles and magnetic flux into the nebula corresponds very nicely with the magnetic field vector that one sees in the X-ray polarization. Another early observation, indeed, the first observation that was released for images, or to the public of Chandra images, is this image of Cassiopeia A. Cassiopeia A is a supernova remnant. It was known to be a core collapse supernova remnant, the type that comes from a very massive star collapsing, as opposed to the merging of, as opposed to the collapse of a white dwarf. And something that wasn't known is where that crazy pulsar is. You know, we just saw what the crab looks like. Ridiculously bright pulsar, point source. The neutron star for Cass A had never been found. Now, maybe the central region of the explosion collapsed to a black hole. That's possible. But as soon as this observation was taken with Chandra, with a bunch of people huddled around a screen to see if the imaging actually worked well, I wasn't one of those people, but I'm told that was a lot of fun. That point source was immediately identified. There's the neutron star in Cassiopeia A. Not only is there's the neutron star in Cassiopeia A, there is a neutron star that's only a few hundred years old that is nothing like neutron stars that we had seen before, okay? We thought that they were all highly magnetic, fast spinning, flinging out relativistic outflows of relativistic particles. No, this one isn't. And since then, Chandra has found others that are similar. Now, the remnant itself is of considerable interest, obviously to me because I do this kind of work, but because it really emphasizes some of the types of things that Chandra can do. If you take the spectrum of the entire nebula remnant, you see the spectrum that I've got over here to the right, and you can see discrete lines of silicon and sulfur and argon and such. I highlight over around 1 keV, excuse me, a broad region that is iron K, that's dominated by iron K emission as well. And what you can do is the trick that I described before, take different energies of photons and color them in different ways to see how they're distributed through the remnant. And when you do that, you get this. This immediately lets you see that over here in this purplish reddish area is heavily iron L dominated material. That's interesting, right? We all either learned or taught that when a massive star collapses, what's happening is that the iron core, the very, very center, is the last thing that existed. And since it doesn't produce excess energy when fusion occurs, that's what causes the onset of the collapse. So that's what's going on at the very, very center. But the iron in the explosion is way out here on the edges. So this immediately tells dynamicists who are studying supernovae that they have to be able to have enough instability that they can flip the ejecta layers entirely. If they can't do that, they can't match real supernova remnants. In addition, you see this thin blue line or rim around the supernova remnant. That, if you look at the spectra of individual regions, is synchrotron emission. And that synchrotron emission is from electrons whose energies are 50 to 100 tera electron volts, okay? This is evidence of the acceleration of cosmic rays by supernova remnants. You can take the ejecta material here. This is all the colored stuff that you see here is primarily from the guts of the star that were flung out in the explosion and expanding. You can add up the different types of material that you see, make some assumptions about the filling factors in the remnant and such, and make a census of the ejecta. And that can lead you to an idea of what the progenitor star was that blew up. And that's been done. Una Huang and colleagues did that a long time ago, came up with about, I think, if I remember this correctly, I'm just looking to see, well, there's people in this room. I was looking for Dan Patnow, but there's others in this room who can also tell me I'm wrong. I think it's about 3.5 solar masses of ejecta material. From the dynamics, the expansion of the remnant, which is also one can measure through Doppler shifts on the lines, one knows that the total amount of ejecta, actually I think it's about 3 solar masses, and I think that the total amount of ejecta that one infers is about 3.3. So there's some missing. This is great. We can add it up, we can find the different types, but there's some missing. Why is there some missing? Well, because the reason that this ejecta is all lit up is because the explosion happens, it expands out into the interstellar medium, which is not empty, right? It sweeps up material and decelerates as a result. These ejecta, which have adiabatically cooled really, really fast, so they're all cold, they feel this pressure from the decelerating blast wave, and this pressure wave comes back in, a reverse shock, and heats the ejecta. That's why it's glowing. But that reverse shock has not gotten all the way back to the center. It hasn't gone through all the material. That's why there's some missing here. How could you ever find the ejecta from the center of a supernova remnant if it's cold? Well, you could look at it with an infrared telescope, okay? So this is Cassiopeia A with James Webb. And indeed, if you look at, you can't see this with the window, with the shades open either. It's very, very faint. Go look at the paper by Milosavljevic and all. It's got really, really wonderful images of all of this. But you can see the cold ejecta in there. So putting James Webb and Chandra together completes the picture of Cassiopeia A. Not only that, but James Webb, in doing this, the team found this crazy-looking structure, which in the colors that they chose is green. And so possibly because Danny Milosavljevic was a postdoc here, became known as the Green Monster. And for those of you who don't get that joke, you need to go to Fenway Park. What is it? Well, originally the team looked at it and thought, that's kind of in the middle. Maybe that's ejecta too. You can find that same structure if you work at it over in this Chandra image and extract the spectrum from it. We did that and compared it with shocked circumstellar medium way out on the outside and concluded that that material is actually circumstellar material. And not only that, but there's some Doppler shifts in it that suggests it's actually out on the front side. So Chandra and James Webb put together can really unfold what's going on with Cassiopeia A. One last thing before I start bouncing past this subject is also to demonstrate how crucial the Chandra images are for understanding results from other experiments. So the IXB telescope looked at Cassiopeia A. There's the image. Remember the story I told you early on about not all X-ray mirrors are the same? That's the outer part that says forward shock. That's all this area. But it's all blurred together because those optics aren't as high quality as Chandra's. But the polarization signal in that ring can be measured. And it's not zero. What's complicated, though, is to figure out what you're looking at. And luckily, that's what Chandra does for you. It forms what we refer to as the ground truth for these observations. There's two components to the spectrum. There's the synchrotron emission from those thin rims, and then there's the big mess of thermal emission from all that hot ejecta. That thermal emission is not polarized. It's just hot, optically thin gas. The only polarized part of this is the synchrotron emission. So by using the Chandra spectrum, you can figure out what fraction of the synchrotron emission is actually polarized. Or I should say, you can figure out the polarization degree for the synchrotron emission. It's important for two reasons. One, maximum polarization degree for synchrotron radiation in the X-ray band is about 70%. Okay? What's measured for Cassiopeia A, this is a polar diagram where the radius is the polarization degree and around the azimuth is the angle. the polarization degree is about 3.5%, not 70. That's interesting for a reason I'll explain. And the angle here is the polarization direction, which is the electric vector of the photons, which for synchrotron radiation is perpendicular to the magnetic field. Stay with me. So this is the angle relative to radial. 90 degrees means radial magnetic fields, okay? So what this is saying is that the magnetic fields that we're seeing in Cassiopeia A are radial. The polarization degree is low. And why is that important? Well, first of all, to accelerate particles at shocks, you need a lot of turbulence and amplified magnetic fields for that matter. And if you have a very turbulent magnetic field, then you're not going to get 70% polarization degree. It's going to be washed out a lot from that turbulence, and that's exactly what these data are showing, that there has to be a lot of turbulence because the polarization degree is so low. The other thing we know is that we are probing the magnetic fields with this really, really close to the shock. Now, you know, how could you possibly say that from that image? You can't. But you say, I know what's in that outer rim. It's this. And those synchrotron radiation photons are all coming from those thin rims. So this is showing that the magnetic field is very turbulent on exceedingly small scales right outside the shock. And that tells us a lot about particle acceleration. I'm going to skip this because I want to go out of the galaxy for some people who don't spend their entire lives there like I do. This is one that you're more familiar with, though. Since I was on neutron stars, we might as well keep talking about neutron stars. They can form in binary systems. They eventually will gravitationally in spiral after losing gravitational waves and merge, forming a neutron star merger, a short gamma, and accompanied by a short gamma ray burst. And if you're lucky, detectable gravitational wave signals, okay? And this is from GW 1708-17. Chandra looked at GW 0817 right when everybody else did. You see on the left the observation that was taken 2 days after the event, nothing detected, okay? But several days later, the source is detected quite well. And the understanding of what's going on here is that the merger formed an explosion. The explosion formed jets. The jets were not directed at us, and so we are looking at this off of the jet. But as the jet sweeps up material, it has a broader angular distribution on the sky, and then we can begin to see this afterglow of the jet. And so one can model that picture. This is what that swept up material from the jet should look like, and as time goes on, the signal will decay down. But note that Chandra kept looking at this long after other telescopes couldn't see it. And eventually, it didn't follow this curve anymore. Eventually, the afterglow faded away, but there was something else there. And the something else that's there is either the swept up material from the central explosion itself, or possibly emission from a magnetar that was left behind. Okay. Into our galaxy. This is a Chandra observation of the center of our galaxy. For reference, the galactic plane is shown here. You can see in red some lobes of gas up above and below that plane. The top panel looks at 3 million seconds of staring at Sagittarius A star. But they're all pasted together. It was done in many different observations, so there's gaps between the time, and they just smushed it all together and make it look like it's all continuous. But what you want to notice is that you have a very low level flux and occasional flares, okay? There's on the left at the top there's a tiny blue region that's blown up at the lower left to show some flares in that time interval. And then there's another wider blue region that's blown up on the lower right to show you, wow, this is the most boring supermassive black hole I've ever seen in my life. So this is a 5 million solar mass black hole. at the center of our galaxy, close enough that you'd think we'd be able to get some interesting information, but it's just not very active. It does flare, so that's not it, okay? It's so faint that in this little movie, each frame doesn't really capture that little flux. There's a nearby magnetar that's shining, but during this September 2013 observation, it suddenly underwent a flare where it increased in flux by about a factor of 200. But largely, this is just a currently very inactive black hole in our galaxy. As I said, there's these apparent lobes of hot gas that suggest perhaps former outbursts, that maybe they're correlated with the Fermi bubbles and the hot gas seen in E Rosita, or maybe they're just hot gas that's kind of spherically distributed and the dust in the center of the galaxy is absorbing the middle of it. It's not clear. But we certainly know that our galaxy has had past episodes that were much more interesting and active than our current one. And an interesting aspect of the characterization of the emission from Sag Star is that compared to other black holes, which follow a fundamental plane, is how it's referred to, as behavior between the X-ray flux, the radial flux, luminosities, I should say, and the central mass of the black hole. Sag Star in quiescence is way off of that fundamental plane of black holes, and it's not obvious why that is. It's entirely possible that there isn't like steady accretion going on at all, that what we're seeing is sometimes we're seeing flares, and the other time what we're not seeing is a whole bunch more little tiny flares, and it's just not behaving exactly the same way as the rest. I'm going to skip that as well. We certainly do know that other supermassive black holes form much more impressive jets and are much more active than Sag Star. This is Slane, which is 10 times, whose black hole is 10 times as massive as that in Sag Star. And to the lower right, that some of you can see, is a familiar image of it in the optical, where you see this dark absorbing band across it. And in the X-rays, you see that absorbing band very clearly in the bluish region in the center as well. But what's not at all obvious in the optical, but it is glaringly obvious in the X-rays, is this amazing relativistic jet and this huge lobe with a shock back in this direction that obviously is indicating some massive outbursts of activity from this system in the past. When one puts the gratings in when looking at this with Chandra and looks at the nucleus, you can see in the plot on the upper right the iron K line at 6.4 keV from 3 different observations, let's see, I guess 4 observations, and then the total from them. And you know, if you look at that for not very long, you can see it's not symmetric about the expected position of the iron line. That expected position takes into account the motion of Slane itself, and this is clearly redshifted. And you can see that here as well. It's showing exactly the same thing. And so the interpretation is unclear, actually, but either the nucleus has some kind of outflows that are dominating the spectrum and showing redshifts, or the nucleus itself is moving relative to the whole ensemble. There are other examples of these kinds of massive outflows from supermassive black holes. This is M87, which has a very well-known bright jet. And if you take a close look at an image where I've burned out, or someone, actually Bill Foreman has burned out the jet here, you see all of these structures in the outskirts of the region around the supermassive black hole, these loops that are almost surely formed from previous outbursts where there's an explosion of activity and it just forms a ring that floats buoyantly up into the circumgalactic medium. And you can see that it's on all sorts of different scales, including, if you watch it closely enough, one from a long, long time ago. So this system and others like it have very, very significant energy input from their supermassive black holes that impact their surroundings. And what does that mean? Well, here's an image of the Perseus cluster, which has very obvious cavities that are from some sort of past activity. An early conundrum from the studies of clusters of galaxies with Chandra is that one expects that in a cluster of galaxies, they're denser down in the core. Since rho is higher, you should have higher emission. That higher emission should make it cool. That should drop the pressure. That pressure should make colder gas rain in from on the outside onto the galaxies in the inner cluster and trigger star formation. So you should expect to, in these kinds of clusters, to have a lot of star formation in the inner galaxies, and that was not seen for a lot of them. Why not? Because they undergo these episodes of massive injection of energy that blow away the gas and prohibit it from starting off those star formation episodes. Last on the supermassive black holes, if you want to keep going farther away to look at them, you learn some interesting things. So here's an observation of a cluster, Abell 2744. Akash, you can just tell me when I get this all wrong. Which JWST used as a gravitational lens to magnify the field behind it to look at really, really distant galaxies. And so in the panels to the upper left, the one on the right is an image from JWST finding a galaxy behind this cluster at a redshift of about 10. It's kind of just a little speck, but I can assure you that you can see it very clearly in the image. And so Chandra observations led by Akash and colleagues targeted some of those galaxies and discovered bright X-ray, not bright, what am I saying? Discovered, remember what I said before? A few photons with the background of this detector, that's all you need. So discovered photons from that, which when considered in terms of their distance and count rate, are consistent with emission from a supermassive black hole with a mass of about 4 times 10 to the 7 solar masses at a redshift of 10, okay? So this is kind of wild. That's like 500 million years after the Big Bang. And you've already got the formation of the supermassive black hole of 40 million solar masses. That's pretty rapid supermassive black hole formation. And it puts very significant constraints on models for which supermassive black hole formation either happen from slow processes where stars, go through their lives and eventually collapse into and merge into a supermassive black hole, or massive black hole seeds that condensed from very large structures early in the universe, which this certainly seems to suggest. This is consistent with results from another similar system found in this same field. Okay, finally, structure and cosmology. So this is the cartoon for those who don't know this already. But we have this universe that at this current epoch we believe to be consisting of 75% dark energy, 21% dark matter, 4% normal matter. And let's think about the normal matter and the dark matter over here to begin with. The dark matter is complicated to study because, except for gravity, it's non-interacting. So, it doesn't heat up, it doesn't radiate, it doesn't come home at night. It's just not very, it doesn't cooperate very well. So nonetheless, it's out there. So here's an optical image of a cluster of galaxies. These clusters of galaxies, they're filled with galaxies. That's why in our inventive ways of naming things, we call them clusters of galaxies. But we also know that they're filled with dark matter. We just can't see it, but the dark matter dominates the mass contribution here. And so one can go through this field and look for lensing effects lensing effects on background sources to make estimates of where the distribution of total mass is in this cluster. And it's actually in two different clumps, which isn't a surprise because I believe that optical studies of the velocities here already knew that this was a merging galaxy, so merging cluster. So you've got a sort of a cluster merger. Here's a bunch of the mass concentration. Here's a bunch of the mass concentration. Since they already, you could imagine, that these are going away from going up like this. But since they've already merged and interacted based on the other dynamic information, the likelihood is they sort of pass through each other like two ghosts, okay? And what we're seeing here is dominated by the dark matter. The dark matter just goes by. Yes, it interacts gravitationally, but it doesn't interact in any other way. There's no collisions. So those two masses just pass through one another. So that's boring. But this isn't two ghosts passing through the night, because the dark matter also has high temperature gas that's been stripped off of the other galaxies over time, and is a bright emitter in X-rays, okay? So instead of thinking of this as two ghosts passing through one another, think of it as two ghosts holding cats going through one another. These things go through and they separate, but in the middle you've got a complicated snarl of activity. And you can see that this is plowing through the gas of the other one by this wonderful bow shock here. And you can see the very distinct evidence that the dark matter and the baryonic matter are separated because one is interacting and one is not. Okay, finally, on the dark energy part of that diagram, this is work by Alexei Viklinin and his colleagues. Taking a look at the mass distribution of clusters of galaxy at different redshift bands. So this is in a redshift band from 0.025 to 0.25, and it shows the number of clusters as a function of cluster size. So of course, there's a lot more small ones than there are big ones, and that's what the curve looks like. The model is a fit to something that does not have a cosmological constant, okay? And if you take that same model and you say, okay, fine, I can make a prediction with this. If that's the model, I can make a prediction of what this curve should look like in another redshift band, right? So this model says that if you looked in this redshift band from 0.55 to 0.9, you should find a distribution of cluster masses that follows that, okay? But with Chandra, you can measure them, and that's not what it looks like at all, okay? But if you instead fit the first one with a cosmological constant, and then you apply that same model to the data at the other redshift, it fits it perfectly well. So this demonstrates using clusters that you have a cosmological constant, that you have the presence of dark energy. So that's the whirlwind tour. Like I said, I've left out a lot. The story with Chandra is that it's still doing all these things I've described. It's working wonderfully. We've had more than 540 million seconds of observing, published over 10,000 papers, about 18 PhD theses per year. And there's all sorts of other things, new things that come up that we continue doing with Chandra, as I said, that I haven't been able to talk about. For example, something that I didn't mention is that you can look at microlensing events and find ways to probe structure on very, very tiny scales, smaller scales than the resolution of the telescope because they're magnified by a lens. And right now, When I was eating lunch, we were in the radiation zones with the observatory, but right now we're observing MGJ 2019 plus 1127. That's a quasar system that is gravitationally lensed. In the X-rays, you can see multiple sources from the gravitational lensing as well. Now, you know that in a gravitational lens, if you have one background source, you can get multiple image sources. But what you see in the X-rays is actually not the images from a single source, but rather the images from two sources. And those two sources are close together. You'd never be able to see them with another X-ray telescope, only with Chandra. They're very close together. But they're from an image that's magnified 300 times by the gravitational lens. So they're, let's say, an arc-second apart for our eyes. They've been magnified by 300. So we're seeing milli-arc-second separations and potentially the structure on those scales from this system, which may well be a dual AGN system, and we're looking at both of the nuclei merging at only a couple of billion years after the Big Bang. That observation is going on right now. The principal investigator is the person who hired me, Dan Schwartz, and I'll end here. Take any questions that you have.
Well, thank you, Pat. And please wait, I'll give you the microphone to ask your question.
I'd like to just comment on the first slide you showed.
I got it wrong right from the get-go.
To me, the most amazing thing about that is that the distribution of X-ray counts is symmetrical about the magnetic field line. And somebody decided that that was actually an X-ray source and not particles precipitating. And I think it took great insight and great courage to publish.
So, yes, I think you're absolutely right. And I read the paper again last week, just to catch up. It's amazing, because they talk about that. I mean, they say, how are we getting fooled? What could this possibly be? They talk about, at some point, geez, there could be shocks. Could it be relativistic electrons? What would you get from hadrons that were produced in that way? They just go through the whole thing in like 4 pages. It's ridiculous.
So, somebody asked about some topic that Pat didn't talk about that you know about.
Thanks. Uh-oh.
Pat, that's a beautiful talk. So, but you did. What can you tell us about the great discoveries from Chandra, thanks to its resolution, which is, of course, it's incredible when you see that half-arc second figure on our wall up there. I remember seeing that when it was first posted, and it just blew my mind and everybody's mind that, my God, Leon did it.
Yeah, that's exactly right.
But there's a lot of new science that's come from that.
Well, there is. I tried to identify some parts of it, like being able to tease out neutron stars in the field of a diffuse haze of X-ray emission, or finding the torus structure in a pulsar wind nebula. Obviously, the resolution of the diffuse background into a bunch of point-like series of black holes is important. Identifying individual sources in globular clusters so that you can separate them from their companions, do timing on them and/or spectra. There's just too many. Yeah, well, yeah, no, I mean, it's globular clusters, for those of you who have looked at them with an optical telescope in our galaxy, they're not that big and they're really, really dense. And if you look at them with Chandra, you can tease out those individual point sources. And that resolution is absolutely Absolutely crucial for identifying individual sources in the middle of our galaxy, for being able to resolve out the point sources in other galaxies so that you can take the residual emission and characterize the interstellar medium. It's just crucial in all those areas.
So Pat, that point source in Cas A, you kept calling it a neutron star. Do we really know that? I mean, is there a clear signature that it's a neutron star?
Well, it's a good question. There is, first of all, no pulsations. So we can't, no evidence that it's rotating. No surrounding nebula. So far, that's not arguing for it to be. But what else is it? It's not ejecta. We have good spectra of it. There is no lines there. This isn't just some clump of ejecta. We can see it moving. We've measured the proper motion of it. We have looked at it, and now I'm saying we as the astronomical community. The astronomical community has looked at it very carefully in the infrared for any evidence of infalling material that might be associated with being in a accreting black hole. Instead, there's nothing. There's models of the emission that invoke a neutron star with an atmosphere over it that seem to describe it pretty well. We see its flux decreasing in time, similar to the cooling curves that I mentioned early on about cooling neutron stars. So it's anecdotal, but it's, yeah.
It's very fabulous. So in the slide of Perseus cluster, I noticed that the cavity in the actually smaller scale and larger scale are slightly misaligned. Can it be that there is a precision jet going on there?
That's a question that I'm willing to bet anything that somebody else in the room can answer better than me. I would have guessed that those were from different events. Do we have any Perseus cluster people in here who would suggest otherwise? I'm guessing. I'm going to turn it over. Scott, I see you moving. I see cluster people around here. I'm going to guess that that's those are from different outburst episodes.
I think she's asking why aren't they aligned?
Well,
Yeah, is it in precession or ice?
Yeah, well, that's a good question. I mean, these aren't aligned either, so I'm assuming it's either precession, well, probably, I guess I don't know what else it would be. I can't imagine that you suddenly shoot a jet out in the equatorial region, so I suppose. Binary. Okay, binary as well, yeah, that's a good point, Dan.
Thank you for the insightful talk. I briefly read about Chandra being used to look for some missing baryons in the intergalactic medium. Can you provide some insights into that line of research?
Well, I don't know too much about it, but it has indeed been the case that there have been spectroscopy measurements of bright flaring AGN to look for absorption features in the spectrum. And the last time that I looked into this, there was something that, this has been done a number of times and it's been a bit controversial. There have been times when they're not big absorption features, okay? And so there have been times when there's dips and people were pretty excited, and then others had other data that didn't look so good, and so it was a bit uncertain. The last time I saw it, there was a, let's say, credible 3-ish sigma kind of detection. I don't know if others know better than that now, but it's not done with high precision yet. I think that the people in that field would argue that it has been detected at least once.
Okay, thank you, Pat. Let's thank Pat again.